Okay, is this any better? Hopefully this will. I do see it now triggering on the my Streamlabs. Okay, cool. All right, then I will go ahead and start over, I guess. So awesome. Glad that works. So basically, as I kind of went through this program problem, I was just kind of looking at the numbers and trying to figure out what quantities they represent. So just looking at the units of those three numbers, you should be able to understand that those represent volume, pressure, and temperature, respectively. So hopefully that's okay. Sorry about the audio issues there. I'm using a different computer today, and apparently it did not like this microphone. So, all right, cool. So that's really all I said. Just kind of mindless intro things at the start, as always. So we're good. All right, so with that in mind, let's go ahead and work with this problem. So now that we have V, P, and T, we know that the one that we're missing is N, right? The moles. And we know that the question is asking for mass, right? And we remember that we can go from mass to moles or vice versa. So let's go ahead and plug these into our formula. So as always, we have PV equals nRT. That is our ideal gas law. If we solve this for N, that will be PV over RT. And so we can solve for moles now. So I've given us, all very friendly units to work with here. These are all units that we would want to have our quantities in. Of course, just like before, if you were given torr or millimeters of mercury or Celsius or cubic meters or something, you would have to convert these all to liters, atmospheres, and Kelvin. So just remember the units are important here. All right, so with that, let's go ahead and plug all this stuff in. So our pressure we saw was 3.69 atmospheres. We have a volume of 2.62 liters. We have R. All those units there, liters, atmosphere, and moles and kelvins. And then the temperature was 358 Kelvin. So looking at the units here, atmospheres cancels, liters cancels, Kelvin cancels. We're left with 1 over moles, which is the same thing as moles, which is what we're looking for, right? So let's go ahead and calculate this fun stuff. I do recommend that you actually do these on a calculator or whatever you're going to be using on your exam, just so you are maintaining your kind of like muscle memory with these things. Just helps it go faster. Divided by 58. Okay, so all that fun stuff. It looks like I got 0.329. That's enough because that's all the sig figs we need. And the next one was a 0 anyway, so it's okay. All right, so with that, that's how many moles we have, but it asks for mass of nitrogen gas. So in that case, what we have to do is take a look at the molar mass of nitrogen, right? So just remember, nitrogen gas is N2. Don't forget, nitrogen is diatomic. It is one of our Hofbrinkel elements. So don't forget that 2 needs to be there. We don't ever really see nitrogen atoms hanging around at this level of the atmosphere, at least. So we're going to be dealing with N2. All right, same thing if we were to see oxygen gas or hydrogen gas or chlorine gas, those would all have a 2 with them. Okay, so that being said, the molar mass is going to be 28.02 grams per mole. If you look on the periodic table, it tells you 14.01. That's for one nitrogen, but since we have 2 of them, we have to double it. So if we go ahead and do this problem, We had that many moles. We'll put our grams on top to cancel out our moles. Oops, I can't copy numbers properly. Grams over 1 mole. And so if we do this, let's see, let's go ahead, times 28.02. You get 9.22 grams. Hooray! So you can figure out how much your things are going to weigh. And remember, our gas laws do work for everything. Wow, this computer, I've noticed I have a lot of like the blue eye thing going on. I have like the blue light shielding on my glasses, and so it reflects blue light, and so it just makes me look strange. It's pretty cool. So, anyways, I can also see I have not shaved in quite a few days. Shame on me. Alright, anyways, any questions on that one? Hopefully. I'm actually in LA right now, and so I'm using my computer down here. So, yeah. And so that's why I'm obviously in a different room than I normally am. So, and the lighting is all different, and it's just a pain. So, after I, died from the COVID vaccine last week, I was just like, okay, I can't take care of the dog, so I came back down to LA for a bit. So, I'll probably be going back up to Ridgecrest today, so, because it's raining down here. And so, blah. I certainly did, yeah. I was, so about like 12 hours like after I got the vaccine, I started getting like chills and stuff. And then it lasted about 30 hours or so after that. So I basically slept the whole day on Thursday. And then Friday, like I was okay. I was just kind of like tired still. So that was it mostly. I was just kind of tired and achy, so flu-like stuff. But thankfully, like no respiratory effects, so I could breathe through my nose. That's always a very good thing, right? You just hate when you're sick and you can only breathe through one nostril. It just drives me crazy. So I'm glad I didn't have any problem with that. So, but yeah, so definitely when you guys are able to get it, take a day off or something afterwards, just to it happens. It's better than getting COVID, right? So. Who knows? Having extra rest is a good thing, maybe. So, anyways, yeah, I basically like woke up, fed the dogs, went right back to bed. So, so like forget it. Alrighty. Anyways, let's go ahead and. Oh, awesome! I'm glad you guys are on the schedule there. Cool. So let's see what we can do with more stuff with this gas law. So let's just kind of write this out here. The ideal gas law, which is PV equals nRT, can be used to calculate the, let's just say the fourth quantity when given three of P, V, N, and T. So when you have three of those quantities, you can figure out the fourth one. So if you're given P, V, and N, you can calculate T, or if you're given P, N, and T, you can calculate V. You can just, if you're given three, you can find the fourth one. So that's what this law is really good for. It can also be used for more advanced things that we'll talk about in 111, like you can calculate density and molar mass using the equation, but we don't have to worry about that for this class, so lucky us. That being said, what often happens is we end up wanting to change something about these. And we're going to see that we're going to be using this same law, but in a different form for when quantities are changing. So we're going to see like what happens if we take something from a container that is, say, a 10 liters and move it to a 20 liter container. Or if we compress it, changes volume, what would happen to the pressure? Or if we heat it up, what's going to happen? And so we're going to see that we can kind of mess with this equation a little bit to see what will happen when we change certain quantities here. So we're going to see that all of these will equal R. That's the whole point of the universal gas constant, right? And so this is going to be true for any quantities of these four. So for any gas, right? And we can say that maybe this gas has, we can just kind of arbitrarily decide to call all of these just subscript 1. You know, so for gas 1, it has a certain pressure, certain volume, certain moles, certain temperature. And those all have to equal R when you plug them in here. And so, we'll just say that's gas 1. But we also know that for gas 2, or whatever, sample 2 or whatever, those will also be equal to R, right? So this is also true for gas 2. Could be the same gas, just under different conditions. Could be a completely different gas. Doesn't matter. And so since they both equal R, we can set them equal to each other. So we can put all of these equal to each other. Not R2, T2. And so we can see that we can kind of look at basically the conditions of 1, whatever those happen to be. So whatever we're going to start with, your kind of initial conditions. And so this can be the same gas. So we can say, okay, if we're going to change the volume, we can see what happens to the other 3. Or maybe we're going to change 2 of these things. We're going to change the volume and the pressure. What's going to happen to the temperature? And so we can see we can use this to mess with our properties for the gas. Now, one last thing with this is very often we often will just omit N from this equation, and that's if you're dealing with the same gas, like the same sample. Because it's typically not common to change the moles of gas. Typically you're taking the same quantity of gas and throwing it in a different container or heating it up or something, but you don't typically add gas to it. So very often people will omit N from this equation. And if you do so, if you just get rid of the N's, because if they're the same, then we can just get rid of them, we often see this equation take this form, where we just forget about the N's. Just get rid of them. This is called the combined gas law, by the way. And this is used for when quantities are changing. So we can see how to use it. Let's take a look at, how about we say a gas at 12 liters and 6.22 atmospheres and 300 Kelvin is moved to a 4.2 liter container. Oops. At the same temperature. We can see what is the new pressure. So we see here that we have a gas at certain conditions, and we're going to change one of them. And so with that, we're going to be able to see how we can kind of manipulate this equation to figure out what the new quantity that we're interested in is going to be. So again, all this comes down to is taking a look at this word problem and kind of seeing what bits are important and what those represent. So it looks like, of course, if we're given liters, that means it's some sort of volume. For atmospheres, it's some sort of pressure, and temperature, of course, would be Kelvin. And then another number we have is another volume. And so this kind of problem when we're dealing with multiple volumes or multiple pressures or whatever, it's important that we kind of keep track of what's what. So we might call all of these our conditions 1. So we're starting with our 12 liters and our 6 atmospheres and 300 Kelvin. That's all at kind of time point 1. And then we're going to see that we're going to move it to a new volume, which will be our second volume. And so this equation that we've written here has 6 variables. So we would need 5 of those to solve it, right? However, I see here that we only have 4 quantities given to us in this problem. But what we have is a secret hidden other quantity in here. It's not given a number to us directly, but we see that we have the same temperature, which tells us that T2 is also 300 Kelvin. So sometimes, some of your quantities may be hidden as words instead of directly given as numbers. All right, and of course the question is asking what's the new pressure, so we are solving for our pressure at time 2, or conditions 2, whatever. Of course, it doesn't matter. You could call the first set of conditions V2, P2, and T2. It doesn't matter. It's really arbitrary, so it'll work either way, but typically we start with the initial conditions as 1 and our new conditions as 2. So let's go ahead and take a look at our equation again. All right, so I'm just copying it as above. Alrighty, and with that in mind, we can go ahead and solve for P2. I like to do that. I like to solve for the variable and then plug in the numbers. But if you like to do it the other way, we just plug stuff in right now and then solve for it, that's fine. That'll work. No problem. But if you solve for P2, you get P1 V1 T2 over T1 times V2. Right, so we multiplied both sides by T2, we divided both sides by V2, and this is what we end up getting. And therefore, if we plug in our numbers, our pressure 1 was 6.22 atmospheres. Our V1 was 12 liters. 12 liters. Our T2 was 300 Kelvin. T1 was 300 Kelvin. And V2 was 4.20 liters. So notice, for unit purposes, liters cancel, Kelvin cancel. So we are going to end up with atmospheres, which makes sense because we're looking for a pressure, right? And so another thing we might notice is that we have, in fact, the same temperature. So we can just completely get rid of that at all. We don't have to worry about calculating that. And so it just comes down to these last 3 numbers. And so we can just go ahead and plug them into our handy-dandy calculator. Let's see, what do we get? So we have 6.22 times 12 divided by 4.2. Doing this, we get 17.8 atmospheres. Doing this. So with that, let's see, does this answer make sense? And it's always a good idea to kind of like look at stuff and say, hey, is my answer reasonable, or is it just completely like nonsense? And so if we look at what's happening in this problem, the only thing that's changing is we're taking it from one volume and taking it to a smaller volume. And so if we kind of remember back to our analogy, that's compressing the container, making it smaller. So are we expecting the pressure to go up or go down? Do we think it's going to collide more with the walls or less with the walls when we squish it? And we should expect it to go up, right? Because now that we have a smaller container, molecules have to travel less between collisions on the walls. So we're expecting pressure to go up. And so it does, and so we can see, okay, this is pretty reasonable. And if we look also, we can say, okay, you know what, this 12 and 4.2, that's roughly, 3, right? 12 over 4 is about 3. And so, if we're going to divide our volume by 3, we're roughly going to be multiplying our pressure by 3, right? And so, yeah, again, this looks like, 6 times 3 is 18, right? Of course, 12 divided by 4.2 is not exactly 3, it's close enough. But again, we're in the ballpark here. So this is kind of confirmation for us that we're on the right track. So you can be confident in your answer just by kind of thinking about it a little bit. All right? So just to kind of reiterate when to use this equation, uses, oh, that's nice. Okay, use the combined gas law. PV over T equals PV over T. I guess I'll put the 1s and 2s. When quantities are changing. Alright, there are some cool things you can do with this equation. First thing is, because we don't actually have R in this equation, you can use any units you want. So any units for volume and pressure can be used, but they need to be the same unit on both sides. So that means if you're dealing with, if I had given you that pressure as torr instead, you would get out your new pressure as torr, which is fine. It's a totally usable pressure unit. You can use milliliters instead of liters if you wanted. You can use PSI, you could use whatever bars, pascals, whatever kind of crazy units you like, you are welcome to use those. You do not need to convert them to atmospheres or liters. And so you're welcome to use whatever ones you want there. All right, you will just end up getting your answer out in the same units that you put in. So you can either convert it beforehand or afterwards. If you're given a different unit, that doesn't matter. Notice temperature must be Kelvin. So you must use temperature in Kelvin. You cannot use it in Celsius because, well, let's say we have a gas at 20 atmospheres in a 20-liter container is heated from 0 degrees to 25 degrees, and the pressure is maintained or something, I don't know. It stays at 20. 3 seconds, I guess. What is the new volume? Okay, so if we do something like this, and if we're kind of being, here, in fact, let's go ahead and use torr instead. We'll see it really doesn't matter. And milliliters, who cares? Let's have some fun with our units. Okay, so with that, we can go ahead and try plugging stuff in. So if we have P1 V1 over T1 plus P2 V2 over T2, we're going to see that if we solve for V2, it'll be very similar to our last one. P2 T1. Okay. And let's just go ahead and plug in everything. So we had 20 torr, we had 20 mLs, we had 25 degrees, we have our pressure 2 is 20 torr, and then of course we had 0 degrees. Uh-oh. What's the problem here? Indeed. So if we try to just plug it in as Celsius, we divide by 0, which will make some people very mad. Yes. Or worse, if we had something like negative 10 degrees, we would end up with a negative volume, which doesn't make sense. A volume must always be a positive number. So, it really doesn't make any sense to use Celsius, because Celsius can be negative and it can be 0. But mathematically speaking, that's not allowed for this sort of equation. So we would have to convert it to Kelvin. And so we could actually do that. So we can say instead, let's just now replace our values with Kelvin numbers. So that would be 298 and 273. Remember, to get Kelvin, you just add 273 to the numbers. So adding 0 to 273 will get you there. And then 298 is 25. Okay, so with that in mind, now look what we can do. The 20 torrs will cancel out. Kelvins will cancel out, so we're just left with milliliters. And so let's go ahead and do it. 20 times 298 divided by 273. Alright, we get 21.8. Our units will stay the same as we put them in, milliliters. Alright, so yes, we must always use Kelvin when dealing with gas laws, because Kelvin cannot be 0 and it cannot be negative. And so we can do all sorts of fun math with it. And so we're going to see that, some of the conceptual stuff we'll do a few examples of that sort of thing in a second. The Kelvin is really the only way we can work with those as well. So let's go ahead and analyze this. So we did not necessarily look at the relationship between volume and temperature directly. We had looked at how they relate to pressure, but notice here that we did end up being able to see what happens when we mess with the temperature and keep the pressure the same. So we're kind of throwing the pressure out the window right now. And so we can see that if we heat up our sample of gas, it became a bigger volume, right? We increased its temperature and it expanded. And that makes sense, right? We kind of know that that things expand when you heat them, right? For example, if you heat metal up, it will expand. It's how thermometers used to work, is they would have a strip of metal, and as the temperature changed, it would either expand or contract. And it's so, sensitive to those changes, it would have its little like pointer, and as soon as that metal expanded or contracted, it would move the pointer, and that would tell you what your temperature you were. Or if you're looking at a thermometer even, like especially a mercury thermometer, you know that you have the liquid in the bottom, or if it's an alcohol thermometer, it's the same thing. You know that as temperature increases, it moves up the thermometer as that liquid expands inside. And we know hot air balloons are able to work because gases expand, as you heat them. So as you heat up the gas inside your hot air balloon, it expands and pushes up against your balloon, letting you fly through the air. So this all stuff kind of makes sense. We already know about it, but here it is again. So with science now. So we can see that volume and temperature are going to be directly related to each other. As one goes up, the other goes up. So exciting stuff. So, but that's not really a relationship we looked at. It's just something cool, I guess. There are a bunch of gas laws that fancy scientists have done. Charles and Boyle and Avogadro and Gay-Lussac and who cares? All these other random names for laws. Some chemists like you to memorize whose law is which one. This particular one is, I think, Charles's law, dealing with volume and temperature. I don't see that helps you learn chemistry at all, knowing someone's name. I don't really like to focus on that sort of thing. So, if you continue taking chemistry with me in the fall, I will continue the same. But just if you end up taking 111 elsewhere, you may be forced to learn those names, which I really don't see how it helps you learn the concepts. To memorize that the relationship between volume and temperature is Charles' law, or that between volume and pressure is Boyle's law. Like, I don't even know if those are the right names. So, anyways, rant over. Let's go ahead and see another example. Alrighty, so if the temperature and volume are doubled, what happens to pressure? Alrighty, so this is a kind of very common conceptual question where you're just going to be saying, you're not given numbers, but it says, okay, you know, this is tripled, this is halved, what's going to happen? In this case, it will in fact stay the same, yes. But if you are not so sure about that, I mean, yes, it's awesome if you can just get it exactly, right, just reading it. But what's always a good idea is to use fake numbers. So with this sort of thing, just choose a bunch of conditions as long as they fit what's asked of you. So it's saying that the volume and temperature are doubled. So we can say, the temperature is 1 Kelvin and the volume is 1 liter. And let's say the pressure is 1 atmosphere. Easy. Choose easy numbers. And so if it's saying that volume and temperature are doubled, we can just choose numbers that fit that. So we'll take our initial volume and temperature and double them. Easy, right? Easy with numbers like this. And now we can go ahead and plug it in. So we can see that if we solved for P2 before, we got P1, B1, T2. That's a dot, should be a dot. And then V2, T1. And so we're going to see that we have 1 atmosphere times 1 liter times 2 Kelvin over 2 liters times 1 Kelvin. And in fact, indeed, notice that, of course, our units cancel out, but the 2's cancel out as well. So, and the 1's are just whatever, who cares? We end up with 1 atmosphere. And Eddie is absolutely right that the pressure does not change. And so that's how I think the best way to answer a sort of conceptual question like this. Just make the numbers really easy to work with. If you were really partial to 10, you could use 10 and 20 instead. Or if you like the number pi, go right ahead. And you'll have 2 pi as your, second temperature or something, Choose your lucky numbers, who cares? Or choose very easy numbers like these. And so, while this one was perhaps a little bit easy, we can go ahead and do another one. So if the pressure is triple and volume is quadrupled, what happens to the temperature? So again, make fake numbers. If you're not given any, you have the freedom to choose whatever you want. And you'll see, as long as you're following that pressure is tripled and volume is quadrupled, you will end up with the same answer no matter what numbers you chose. So I would recommend, let's just choose easy numbers. I mean, 1 Kelvin is kind of absurdly cold, but who cares? It's a conceptual question. So pressure 2 is going to be tripled. The volume is quadrupled. Let's see what the temperature is going to be here. So if we solve all this stuff, I guess since we have not solved for temperature yet, we can do that, just in case anybody wants to practice their algebra skills. If we're solving for T2, we would multiply both sides by T2 and divide by P1, V1 and multiply by T1. It's a bit more of a complex solving. Alright, and so now we can go ahead and plug all this stuff in. So we have 3 atmospheres, 4 liters, 1 Kelvin, 1 atmosphere, 1 liter. I guess I should have put the units in, but I was being lazy. Again, with easy numbers, this becomes a very easy calculation. So we're going to see that the temperature overall is multiplied by 12. So whatever numbers you chose, if anybody chose different numbers, if you chose 2 instead, you would get 2, 2, and then 6 and 8, right? And you would see that you would still get the same thing. You would end up with 48 divided by 4, which is 12. And so we look at the relationship. We went from 1 Kelvin to 12 Kelvin. And so we saw that we will end up multiplying our temperature by 12. Whatever temperature you happen to choose, whatever pressure or volume you happen to choose, you will end up with multiplying your temperature by 12. Math is lovely. All right, how's that looking so far? Hopefully not too bad. All right, and so again, you're using this equation for changing things. So if you're changing any of these quantities, you can change just one quantity, you could change 2 quantities. You know, you have a lot of freedom with this. Just one more thing to note with this equation is if any quantity is unchanged, it can be omitted. So if we look back to what we did, where was that? Here. We had the pressures equal to each other, right? The pressure didn't change over this process. And so if we really wanted to save ourselves some grief, we could just get rid of the pressures. We don't have to even worry about them. So just like, remember, we can kind of omit the moles, because moles typically are not changing if you're using the same sample of gas. We just got rid of those from the equation. But if anything else is the same, you can just get rid of those. I'm going to just put it back here just so the notes are complete. I think in this one, we had the temperature being the same. And so if we wanted, we could just get rid of the temperature. That would work. You are totally allowed to do that. So if that makes it easier for you, go right ahead. Or if it's more, some students it's easier to just be consistent the whole time and not get rid of them. No problem. It'll all work out. You'll see that they'll cancel out anyway, so there's no kind of more work or anything associated with it. Okay? So, that's the end of that section, I suppose. Alright, just so you know, there are things called standard conditions. It's called STP, standard temperature and pressure. This is when we are going to be dealing with 273 Kelvin or 0 degrees Celsius. Same thing. And 1 atmosphere. This was developed because way back when people were originally studying gases, in order to kind of make comparisons easy, they would use the same temperature and pressure when doing experiments. And so by doing so, they came up with these conditions called STP, which is what people agreed to kind of work with for doing certain calculations with these gases or gas experiments, just to kind of standardize things to make them easier to compare with each other. And so if you ever see STP, it means 0 degrees Celsius and 1 atmosphere. All right, and something that's pretty common, a common exercise that we do here in chemistry. Before we do that, I should give a little disclaimer. STP is technically actually defined as 273 Kelvin and 1 bar by the International Union for Pure and Applied Chemistry, which is kind of the chemistry gods, I guess. It is technically officially 1 bar, but if you look in any chemistry textbook, you'll still see that they use atmosphere for teaching STP. So while it is technically 1 bar, almost universally people still use atmosphere. So it's just force of habit, I guess. I have done my job in letting you know that it's technically a bar, but for us in this class, we're going to use it as an atmosphere. And remember, an atmosphere is very close to 1 bar. It's 1.03625. So 1.03 versus 1, it's not a huge difference. Anyways, that aside, one thing that's very often calculated is what volume does 1 mole of gas occupy at STP. And let's just go ahead and put some sig figs on there. Still 1 mole. Well, so we're given pressure, temperature, and moles. Yes, you have the right answer. Yes, very good. If we do the calculation, solving for V, it's nRT over P. And that will be 1 mole times our lovely gas constant. Temperature is 273. Pressure was 1 atmosphere. And doing this calculation, indeed, you do get 22.4 liters. And so you can actually do a shortcut between moles and volume if you're at STP. at STP, 1 mole will always equal 22.4 liters. And so it was an easy way for people to say, okay, I need, half a mole of gas or whatever, so I'll need 11.2 liters. Because again, you can't really measure moles directly, and it's very hard to measure the mass of a gas sample, but we can measure the volume very easily. We can have containers that can expand and say, okay, now it's hit this particular volume at STP at 0 degrees Celsius and 1 atmosphere. I know I have 1 mole of gas here. And then from that, you can go ahead and say, okay, now I'm going to use my 1 mole of gas and see what happens if I introduce 2 moles of gas of whatever, and have fun with your experiment. So it's basically just a conversion factor. So at STP, 1 mole is equal to 22.4 liters for a gas. So it is a conversion factor. So again, everything is unit conversions, so go figure. Alrighty. With that, let's go ahead and take a look at how this is going to work. How many liters does 15 grams of oxygen occupy at STP? Well, you are certainly welcome to use the ideal gas law. It will work, no problem. But we have a shortcut. Right? We know that 1 mole is 22.4 liters. And we know that 32 grams of oxygen is 1 mole. Don't forget, oxygen is O2. You do not see monoatomic oxygen. You always see it as diatomic. And so we have 2 conversion factors that will get us our answer. So we start with grams. We're going to want to get rid of grams, so that goes on the bottom. And we'll see that all these units will cancel out. We'll be left with liters. And so, say if I wanted to isolate 15 grams of this thing, I could just measure a particular volume, which let's calculate, is 10.5. So if I wanted to get 15 grams of oxygen, because I need that for a medical purpose or I need it for an experiment, we can just go ahead and extract 10.5 liters of oxygen, which will be that 15 grams at STP. Just so you know, 22.4 liters is roughly a cubic foot. So, I don't know, it's going to be like this by that by that. So that volume there is about 22.4 liters. So if you can just imagine that, it's like a little bigger than a shoebox, right? So there you have it. All right. So it's just kind of a special case. Just makes things easy for us if we have them kind of standardized like this. There's one last bit about this. Yeah, we'll do it. We have time. Alrighty, all this time we've been talking about one gas at a time. But very often we're going to have mixtures of gases. And we're going to see that we can kind of very easily talk about individual gases within a mixture. So, let's see, mixtures of gases. Alright, I have a common gas mixture for us. Anybody know what this is, this particular mixture? Pretty commonly used in everyday life? Well, this, of course, is air. The air we breathe is this mixture. There's also some other kind of smaller proportion things like carbon dioxide, water, or whatever. But this is a very common mixture of air or of gas, right? Something that is present all over the world. So it turns out that we know at sea level the pressure is 1 atmosphere. Right? That's how we've defined 1 atmosphere. And it turns out that the pressure, if we just looked at nitrogen gas, is in fact 0.78 atmospheres. Since nitrogen was 78% of that air, 78% of the pressure is caused by nitrogen. And we're going to see that the pressure of oxygen would be 0.21 atmospheres, and the pressure of argon would be 0.01 atmospheres. And if we add those all up together, we're going to get our total pressure of 1 atmosphere. And so we can see that each gas in a mixture exerts a pressure proportional to its, what shall we say, abundance? So however much your mixture is made out of a particular gas, that gas will have a pressure that is proportional to how much of that gas is in there. Another way of saying this is what's called partial pressure of whatever, gas X. Now let's say gas A. Let me rewrite that. That's called a partial pressure of gas A, whatever that gas happens to be, is something called the mole fraction of A. We'll have a look at what that is, multiplied by the total pressure. This is called the mole fraction of A, where it's just, you remember if we talked about mass percent, we talked about the mass of something over the total mass. Mole fraction, I should write that down. Oops, not giant. Is the moles of whatever you're looking at divided by the total moles. All right, and so that's often can be written as a percent. And thankfully, because we assume that all gas molecules behave the same, we can make this relationship happen. And so we'll really see kind of how to use this tomorrow. We'll finish up the gas chapter. This is kind of the last little topic here when we're dealing with mixtures of gases. And it's really just applying the ideal gas law to a particular gas within a mixture. And just kind of one last thing to throw out there is that the total pressure is going to be equal to the partial pressure of all the gases that are in your mixture. So whatever those all happen to be, if you only have 3 gases, their total pressure should be equal to adding all of their partial pressures up. So partial pressure is a pressure exerted by one gas within a mixture. Total pressure is all of those put together. If we want to see this kind of visually, and let's use purple ones perhaps. If this gas had 5 atmospheres and this gas had 3 atmospheres, if we put them together in the same container, if we just move one from the one container to the other one, we're going to see that that would be 8 atmospheres total. It's pretty easy to tell. So if we just kind of examine each dot as an atmosphere of gas, if we combine those two samples, we'll end up with 8 atmospheres, where 3 atmospheres are given by the purple, 5 atmospheres are given by the blue, and putting them together, we have an overall 8 atmospheres. And so even though each gas contributes its own pressure to the system, overall we can see what the total is going to be by adding those up. All right, so we'll continue on with this tomorrow. We'll talk about this. This, by the way, is called Dalton's law. You do not need to memorize this name, but in case you see the name, you will not be kind of scared of it. We'll see how to use it, as well as this mole fraction idea tomorrow. So we'll go from there. All right? So with that, enjoy your Monday. Have fun, and I guess I'll see you tomorrow then. Alrighty. I will put up your homework at some point, so you can start working on that. Alright? We shall see you tomorrow.